Multiple regression is an extension of simple linear regression that explains the behavior of a dependent variable using several independent variables simultaneously. In investment management, financial analysts use multiple regression to identify relationships among economic variables, forecast future outcomes, and evaluate asset pricing models. Applications include determining drivers of stock returns, forecasting macroeconomic conditions, assessing risk factors, and testing whether additional variables improve existing models. The regression process begins with identifying a dependent variable, selecting relevant explanatory variables, estimating coefficients using ordinary least squares, OLS, and evaluating whether the model effectively captures the relationship between variables while maintaining statistical validity and economic relevance. A multiple regression model is generally expressed as the dependent variable being a function of an intercept, several independent variables, and a random error term. Each estimated coefficient measures the expected change in the dependent variable associated with a one-unit change in a specific independent variable, holding all other variables constant. The intercept represents the expected value of the dependent variable when all explanatory variables equal 0. This ceteris paribus interpretation is one of the most important concepts in multiple regression because it isolates the marginal impact of each factor. Analysts use coefficient estimates to quantify economic relationships and produce forecasts based on assumed values of explanatory variables. The reliability of a multiple regression model depends on several underlying assumptions. The relationship between the dependent variable and independent variables should be linear, and the error term should have a constant variance, a property known as homoskedasticity. Residuals should be independent of the explanatory variables and should not exhibit systematic patterns. Additionally, residuals are assumed to follow a normal distribution, particularly when conducting statistical inference. Violations of these assumptions can lead to biased estimates, unreliable hypothesis tests, and misleading conclusions. Therefore, analysts must evaluate whether the assumptions hold before relying on regression results for investment decisions. Residual analysis is an important diagnostic tool used to assess whether regression assumptions are satisfied. Residual plots compare prediction errors against predicted values or independent variables. Ideally, residuals should be randomly scattered around 0 without any visible pattern. A funnel-shaped pattern may indicate heteroskedasticity, while systematic trends may suggest model misspecification. Analysts also examine normal QQ plots to assess whether residuals follow a normal distribution. In a properly specified model, residuals align closely with the theoretical diagonal line. Deviations such as skewness, fat tails, or extreme outliers indicate departures from normality and may signal potential problems with statistical inference. Evaluating regression model fit requires measuring how effectively the model explains variation in the dependent variable. Analysis of variance, ANOVA, decomposes total variation into explained variation attributable to the regression model and unexplained variation represented by error. The coefficient of determination, R superscript 2, measures the percentage of variation in the dependent variable explained collectively by all independent variables. For example, an R superscript 2 of 0.70 indicates that 70% of the variation is explained by the model. While higher R superscript 2 values generally indicate better explanatory power, analysts must recognize that adding variables often increases R superscript 2 regardless of whether those variables contribute meaningful information. Because R superscript 2 can be artificially inflated by including unnecessary variables, adjusted R superscript 2 is often considered a superior measure of model quality. Adjusted R superscript 2 penalizes the inclusion of additional explanatory variables and therefore evaluates how efficiently the model explains variation. Analysts also interpret statistical outputs such as coefficient estimates, standard errors, t-statistics, p-values, and f-tests to determine whether individual variables and the overall model are statistically significant. A strong regression model combines economic logic, statistical significance, and high explanatory power while satisfying underlying assumptions. Understanding goodness of fit measures and regression diagnostics enables investment professionals to interpret results correctly and develop more reliable forecasting and valuation models.